Hello there guys, we're going to have a good look at the gradient at a point using the concepts of limits. This is the very start of our journey into the wonderful world of calculus in our methods course, thanks to dear Sir Isaac Newton, who invented the whole thing. So let's have a look. It is very, very interesting. So what have I got here for you? I've drawn the graph of y equals x squared on this marvellous little piece of software which I've got, and I've drawn 2 points on that graph, point P and point Q, okay? And what I want to do is I want to use the formula for, or the whole concept of the gradient between 2 points. Now, the gradient of chord between 2 points, okay? See that line there? That line there is the chord, or the line segment joining P and Q. And I want to show you that if we want to get to the whole idea of what is the gradient at the point P on that curve, that makes no sense whatsoever, because you can't have the gradient at a point in terms of our traditional definition of what a gradient is. It's y2 minus y1 over x2 minus x1, or the rise over the run. But at a point, a single point, you can't have y2 minus y1 over x2 minus x1. So we have to go through a certain process of logic using limits to get to what the gradient at a point would be. Now I'm going to move Q closer and closer to P, and I want you to see how the gradient of that line segment between Q and P changes and gets closer and closer and closer to the tangent line at P, as Q gets so close to P to be virtually on top of it. Okay, and that's what we're doing with this whole concept of the limit of the gradient of the line segment PQ as this little red line here, which I'm going to call H, which means just a little bit of difference between P and Q in an X sense, as that H gets smaller and smaller and smaller. Okay? Let's go. Okay, Q's moved down a little bit. Look at the line segment. Now see how it's changing, and I want you to take particular note of this line PQ as Q gets closer and closer to P, and you'll see that it gets closer and closer to the tangent line at P. You see? There it is. Right now it's right on top of P, and it's actually coincided with the tangent line at P. So this is the whole concept of how you get the gradient at a point. It is the limit of the gradient between 2 points as the difference between those points reduces to virtually nothing. That's what you mean by the limit. The limit as Q approaches P, or this little red line here, which I was going to call H, as H approaches 0. And the two X points belonging to Q and P then coincide. That's what we're talking about. Do you get that? It's a really, really interesting, simple concept, but a lot of students just get really messed up with it. So that's it in very simple terms. Now let's see if we can apply this marvellous idea that dear old Sir Isaac Newton invented right back in the 1600s, I think it was. I think he died in 1642, and I know he's buried in Westminster Abbey in London anyway. But enough of all that. Now, what have we got here? We've got, find the gradient of y equals x squared minus 2x at the point Q with coordinates 3, 3. Now see, it's just at the point Q. So we're going to use this whole limits idea to get that, right? Now if you look at this situation here, we've got Q is the point, x is 3, y is 3. And P is just a little bit further on, not very far, not very much further on. So we're just calling it the x coordinate 3 plus a little bit, where the little bit is h. And the y coordinate, therefore, would be using this formula here, applied not to x, but to 3 plus h, our specific value of x at P. So it would be 3 plus h all squared minus 2 times 3 plus h, okay? Whereas this point here at Q, if x was 3, then y would be 3 squared minus 2 times 3, which is 9 minus 6, which gets us back to the same value. So x is 3, y is 3, the same value as the x in this instance. Now, okay, so now we're going to do the gradient of our chord PQ using those values of x and y at those 2 points, okay? So they call that point 1 and point 2. This is what I always do so that you don't get messed up particularly when you're starting out with all this stuff. So I'm going to label this one x1, that's x at point 1. This is x at point 2 and y at point 2, and so now I've got them all. So I've got them all sitting there like ducks in a row, well and truly identified. So now I can use my rise over my run formula for the gradient of the line segment between P and Q. Okay, that's h, that's the little bit. Okay, so that's the x coordinate 3, that's x coordinate 3 plus h. Yeah, now let's go with the maths. Okay, so the gradient of PQ, which I write as a little subscript there, that's m at P. M of PQ is y2 minus y1 over x2 minus x1, isn't it? Well, let's just plug and play now, okay? There it is. Now, it's going to be, that's y2, it's 3 plus h all squared minus 2 times 3 plus h, using this formula here. Yes, there it is. You see, there's the y value at point 2, minus the y value at point 1, which just happened to be 3, as we discovered before, over x2, which is this one here, 3 plus h, right? x2 is, that's it there, 3 plus h, minus x at 1, which is 3. Now let's just get all that fixed up. Looks very complicated, and there's going to be h terms coming out of this, which will cancel maybe, or we can agglomerate with the h terms coming out of that, and the number terms coming out of that. We can sort of get all the ducks together and get them all joining up and simplified. So what do we got? We got 9 plus 6h plus h squared from the square bracket. Minus 6 minus 2h, all from the square bracket, then minus 3. That's all coming from that line there, over 3 plus h minus 3, which just leaves us an h. Now, something amazing is going to happen here. There's a bit of cancelling. See, there's the 9 there, the 6 there, and the 3 there. They all cancel out. Now, you'll always, with these situations, you'll always get a common factor of h on the top line, which you can cancel with the h on the bottom line. So you see what you get there. There's h squared plus 4h all over h. Yes, now cancel a Rooney, and we get that. Okay, we get h plus 4. Now that is the gradient of the line segment P to Q, right? And it's got an h in it. Now, if you want the gradient at the point Q, h has got to be taken to its limit of infinitesimally small and virtually going to nothing, okay, as h approaches 0. That's what the limit means. So the gradient at Q, or else e.g., aka the tangent line to the curve at Q, is the limit of the line segment between P and Q, where that little bit of difference between P and Q in an x sense, that's the h, approaches 0. There it is, right? So it's the limit of the gradient of line segment PQ as h approaches 0, and that will be that. Right now, if h approaches 0, counting it as being 0 would just get you 4. So that, ladies and gentlemen, is the gradient of the curve at the point Q. Okay, when Q has coordinates 3 and 3, that is the gradient of at point Q. And that's the absolute value of the gradient. It's 4. The tangent line at that point Q to the curve has gradient of 4. Okay, you get it. Good. Okay, now let's go with the next one now. In this particular example here, we're actually asked for the derivative function. And the function is x squared plus x with respect to x. Now, this is getting a little bit more general here. So we're not using a specific point Q like we had before, where we knew the coordinates. We're using Q as a more general point. It's just x, and then x squared plus x is the y coordinate, and we're using P is just a little bit more than Q in terms of the x coordinates, just a little bit more. So it's x plus h, and then you apply the formula, the rule for the function, where x is x plus h. You know, the x value is x plus h. So that's the formula, right? So it'll be x plus h all squared plus x plus h. And what we're going to do, the derivative means the general equation as a function of x, which gives you the derivative or the gradient at any point on that curve given the value of x, but it's in terms of x. So all you've got to do, once you get that derivative function, that rule for the gradient at a point x, you just plug any value of x into it, and you will get the numerical value of the gradient. We are going to use the same technique as we used in the previous example with the gradient of the line segment PQ, and then we're going to take the limit as h approaches 0, e.g. P basically just approaches Q and approaches and approaches and approaches so that it basically is right on top of Q, and that's the limit as h approaches 0. Okay, so there's point 1, there's point 2, and that's x plus h. Okay, and the little bit of that little interval there between those two vertical red lines is h, and h is going to approach 0. Okay, here's the maths. M at PQ equals y2 minus y1 over x2 minus x1. We can just plug and play now with the actual values, which we've got. We've got identified and labelled here and here. So that's going to be that. Now, it looks a bit daunting, but look, you just take it slowly and you'll get it out and you won't mess it up. Okay, so let's just expand the top line. That looks a bit menacing, so let's go with that. Is that right? That's x squared plus 2xh plus h squared, yes, plus x plus h minus x squared minus x. Being careful with that minus outside the bracket, it reverses the sign of everything inside the bracket. Now, that's all over x plus h minus x, which just gets you h. Now, we'll clean this line up here, and I guarantee you there will be no terms left without an h in them, and then we'll take it out as a common factor. Yes, that cancels, and yes, that cancels. Yes. That's, yes, see, now let's see if that's right. 2xh, that's this term, h squared is this term, and h is this term inside the bracket. Now we can cancel, as I said, top and bottom with h, and we're left with that. We're left with, wait a minute, what have I written there? Yes, that's right, it's the limit. The gradient at point Q is dy dx, which is the limit of the gradient line P to Q as h approaches 0. Now you can see what that's going to be, right? It's going to be the limit of that now as h approaches 0. So what's that going to be? That's it, 2x plus 1, right? 2x plus 1. Now, you've got your driver's license now to, or your rule, your formula, the key that opens every door to the gradient of any point on that curve with that particular rule, x squared plus x. If, for example, let's just play with one. If you picked x is 3, like in the previous example, you can say, bingo! 2 times 3 is 6 plus 1 is 7. The gradient would be 7 when x is 3. So that's how you do it. That's how you work it out. It comes from that whole gradient of a line segment, business taken to its limit as the difference between those points reduces to nothing, as invented by D.S.R. Isaac way back in the early times, and what a time he had. So, you got it? Good! Now, let's do this one. We've just got a straight limit here, a straight limit to work out, okay? This doesn't look very hard. If we could expand that top line out, and then do the necessary cancelling top and bottom, I think everything will be coming out beautifully. So let's do that. Do you know how to expand a cubic? I hope so. Pascal's triangle to the rescue for the coefficients here. So it's x cubed plus 3x squared h plus 3xh squared plus h cubed. Now, if you don't know how to do that, you better ask your teacher. You better ask your teacher, which might be me, how to do that. And I'll show you the magnificent Pascal's triangle and how it all works. Minus x cubed there over that. Now, there's going to be some cancelling happening there. Yes, goodbye, Mr. X cubed. Is there anything else? There is something from the bottom. Yes, the x's go. Now, we're left with, again, there was no term left on the top which didn't have an h in it, so we're taking that out as a common factor, and now we're going to cancel top and bottom. Good. Now, we're getting down to the business end now. We're just going to, the limit as h approaches 0 means that this term will evaporate, right? And you'll just get left, oh, and that term as well. Yes, and you'll just get left with this little baby, okay? So it would be, that's it. You get it? Yes, it's very simple, isn't it? Not a problem at all. But I want you to get this whole concept of how you get to the gradient, or the gradient of a function at a point, by using this whole limit business, yeah? The limit of the gradient of a chord. Okay, I think there's three more easy peasy ones, and then we can call it a day. What's this? A today, the limit of that thing. Well, that's easy, isn't it? Goodness, just make h naught. Well, what do you get? Come on, tell me. Yes, good. 22x squared, great. What about number B? Yeah, that's also very easy. Look, with these ones, of course, you can't divide by 0. H approaches 0, so you'll always get some cancelling, top and bottom, to rescue us from having to divide by 0, which you can't do. So you see there's an H in every term on the top line. Well, come on, we'll take it out as a common factor, then cancel. And what do you get? What is the limit as H approaches 0? Yes, good. 3x squared. Yes, lovely. And there's two more, is there? Yes. All right, C, what's C? Limit of 3x. Oh, as H approaches 0. Well, there's no H's anywhere, so that's just going to be 3x, isn't it? Get that? Great. And the last one looks incredibly, incredibly trivial, but still we need to do it to make sure you really understand. The limit of 4 as H approaches 0. Well, what is it? Yes, of course, it's just 4, okay? Yes, that wasn't a chore. The answer was 4. And we're having fun galore, and I think that's the end. Yes, goodbye, dear student. Have a lovely time. Go and have a nice cup of tea, and I'll see you in the next exciting instalment in the wonderful world of calculus.